Oh hey guys, it's me Vince, and today's video is on acid-base titration.
So today we'll talk about titration and titration curves. Titration is used to determine the unknown concentration of a solution. There's many types and they can be done by monitoring many things. For example, one could use an indicator, one could monitor pH, monitor electric conductivity, and so on. The indicator will change in color, the pH will have a distinct pH curve, and of course the electrical conductivity will decrease, coming up to an equivalence point, and then increase thereafter. So here we have the classical titration setup. We have a ring stand with a stirring station at the bottom here. We will be using a drop counter. And of course here we have a burette, or in our case a reactant reservoir. And it's got a final initial volume that we can read there and see how much of the solution that we've been used up. We have down here, as I said, a stirring station. And of course in the burette we'll need to know an initial and a final volume. The solution that's in the burette will need a known concentration, and so will the solution in the flask down here at the bottom of the beaker. We have an unknown concentration. Both volumes need to be known. So 3 pieces of information: the volume of each solution and the concentration of one of them. We'll use here a pH probe in our case, and the pH probe or conductivity probe or sensor or indicator, as I said, some kind of device used to measure the progress of the reaction will be connected. And here we're using a LabQuest 2, and we'll be watching the pH curve here, the titration curve. You could connect this to a PC if you want to look at pH, conductivity, and so on. If you are using an indicator, we will need to be judicious with indicator selection. So here's an example. We want to determine the unknown concentration of this strong acid nitric acid using a standardized 0.5 molar solution of potassium hydroxide, which is a strong base. So we do 3 titration trials. You should do at least 3, and here are the results. Now, trial 1 looks like a bit of an outlier. If you have a close look, you can see that it seems like less potassium hydroxide was needed in that trial than it was in the other trials, considering they had equal or just twice the volume of the nitric acid. So here we have the correct balanced chemical reaction, and we'll use trials number 2 and 3 and average the results to get 0.052 liters of the KOH required. That's what we'll start with, 0.052 liters, get its concentration here as 0.5 molar, the mole ratio between KOH and HNO3, nitric acid, and finally the initial volume of the nitric acid. This is what we're trying to determine, the concentration, and it comes out as 1.04 molar nitric acid. So titration curves, they have shapes, and depending whether we're titrating a strong acid with a strong base or a weak acid with a strong base, or something weak, something strong, we're going to see these different curves. The first pH curve here will be a strong acid meets a strong base. So we'll be dropping a strong base into a strong acid here. You notice it's a few features. First of all, the pH starts very low. There's a region of very steep increase here. In the center, that will be the equivalence point. There's curvature that's negative after the equivalence point and positive before it. There's an inflection point there, and that's the equivalent point there. The volume, the pH is about 7 in that case. The second set of curves here, we'll see this is a weak acid meets a strong base once it starts to higher pH. Same inflection points and same steep point in the center of the curve for the equivalence. The pH there was above 7. Here we'll have a strong acid meets a weak base. Notice we start down with pH low again. Here's again the high slope at the equivalence point and the inflection of curvature. This pH is below 7 at equivalence. And here we have a weak acid meets a weak base, and the pH at equivalence to point here depends on the relative Ka's and B's of the acids and bases. So let's just summarize those ideas here, and this summary I hope should get all 4 of these curves on one graph. There's the strong acid strong base curve, pH 7 at equivalence. Here we have the weak acid strong base curve, pH above 7 at equivalence. And here we have the strong acid meets weak base curve. pH will be below 7 at equivalence, so above 7 for the strong one, the bases there, and below 7 for the strong acids. And of course the weak acid, weak base in the green, which will have a pH somewhere depending on the K's and B's. So in any case, in all cases, the equivalence point is at the steepest point of the curve and at the inflection of curvature. In other words, d pH by d volume is equal to the maximum value, that's the first derivative, and d2 pH by d volume squared is equal to 0, that's the second derivative. So we get the greatest slope and the inflection of curvature. If you're using an indicator, we have to select one with a transition point near the expected equivalence point for the titration. So for instance, we'll have a look here at nitric acid and ammonia. Nitric acid is strong, and here we have ammonia. Ammonia is a weak base. So we expect the pH of this to have an equivalence point pH below 7. So we'll use an indicator such as one of these ones here, methyl orange down to bromophenol blue, indicates below 7. The second example, we have a strong base and a weak acid, and that pH should be above 7, so we go in the indicators table here and pick some indicators with an equivalence point above 7. So that's about it for us and titration. For now, at least, there's plenty more to come. Certainly thanks, everyone, and see you soon. Don't forget, of course, to keep your eyes out for our next videos on the topic, and particularly stay tuned for the next lesson in Chemistry 12, lesson number 23, Acid-Base Indicators.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!